All right, so we're going to talk a little bit today about what I'm up to, and I'll try to, it's going to be an overview in terms of 15 minutes, and I think any of you who have actually met me or seen me or heard me here knows I'd be happy to talk to you in as much detail as you can possibly tolerate about any of these things, and I'll be sitting in the back and be here all week. If we go to the next slide, please, or is it up to me to do that? Oh, that's too bad because I like to wander. Okay, thank you. Basically what we're talking about is looking at optimizing spacecraft mass, power, and volume, or the argument size, weight, and volume, the SWAP argument. This is particularly important for CubeSats, which is the topic of interest here, but everybody doing everything wants to make things smaller, weigh less, and use less power. Hopefully head to zero on all these things. But what we're looking at doing is we develop and validate component, board, and enclosure level hardware. Basically, we're headed towards electronics here for the applications that are shown here. Basically, what we're looking at is the idea that thermal management is going to be embedded in the system. I think I made the point yesterday that we have mass. Stuff has to be at mass. Doesn't mean the mass can do one thing. It can be structure as well as hold our thermal control system and some intelligence if we really eat our Wheaties, and we'll talk about that later as well. If we can move to the next chart. I guess maybe I better do it. That's all right. Now, Goddard is in the CubeSat business, and one thing that is going on in the engineering directorate is this idea of a bus or a core module. I think we all know what a CubeSat looks like, so I'll just let this go. If we go to the next slide, because I can't seem to do that. And then our instrument bus, at one time, this was a concept. It's probably morphed into something a little more both tangible, and it's probably changed a little bit. But this is the idea that we would have a core module, some battery, some power, some FPGA, an analog card, and whatnot. And then we would have to mount it, put it in the right size, keep it cool, radiation protection, and again, all the other associated activities that go with that. So if we go to the next slide. So what's the technical challenge that I'm dealing with? Basically, we're looking at making things smaller and embedding thermal control, also with some intelligence. So I'm dealing with two basic foci at this point. One is looking at electronic component packaging. So 3D IC, any of those kinds of allow advanced architectures. We're looking at that, and that will involve embedding thermal control on silicon. And we have an interesting project going with that. And then we're also looking at putting a bunch of cards together, or if you will, making an electronics brick. That has its own thermal problems, its red hard problems, and things like that. But we're looking basically at embedding the hardware, and a very bright young lady named Beth Paquette is working this problem, putting a die together, making it more compact so that it would fit into some standard size, and hopefully something on the order of 10 centimeters on the characteristic dimension, so it would be a CubeSat. Next chart, please. The overview, we have actually a pretty broad program going on. We have fundamental research. This is electrically driven thin film boiling. That has gotten me 2 flights on the Vomit Comet, which is as cool as you think it is. And we're working on self-sensing thermal management using nano-enhanced polymers. Basically, that's carbon nanotubes thrown in latex paint. Hardware development, so we are developing some hardware. I'll talk about that a little bit later. And validation, the aforementioned variable gravity flight. I'll talk a little bit about STPH5, which is an experiment we have coming up. TechCube, which is a CubeSat opportunity that we have next year. Unfortunately, right now that involves a lot of going to church and believing because we have no money, no time, but somehow we'll manage to do it. And then the space station glove box experiment, which is the EHD thin film boiling experiment. Next chart, please. Basically, we're looking at scalable phenomena with intelligent capabilities. So we focused in on electrically based fluid management and pumping, and also electrically based intelligence capabilities. We also do some capillary work as well. That's chip component level EHD, capillary embedded devices, thin film boiling. Also, to embed our hardware involves manufacturing and advanced manufacturing techniques. These guys are magicians. It's all Greek to me. But we're putting these structures together. We're looking at composites. So, for example, electronics box enclosure or something like that, or additive manufacturing. And when you see the EHD pumps, you'll see why we might be doing that. Again, the the self-sensing stuff, and I'll talk about that at the end. And I'd like to get into, but we haven't quite gotten into it yet, numerical techniques. So looking at optimization, electric field analysis, and systems optimization. Next chart, please. These are the boys in the band. I got the coolest job. I kind of the Mick Jagger of it. I get to be the front man, but these guys make it happen. It's Matt, who does our advanced manufacturing. Frank Robinson is a young guy. I'll take credit for bringing him in, and I should at least get a promotion for that. Frank is very talented, probably the most talented engineer I've come across. Mario Martins is a systems genius, and Tim Miller does our microscale fabrication. This is kind of the Darwinian aspect. These are the external partners that I have, Jamal, Hugh Bruck, and Mike O'Hattie. I don't fund them. We write proposals and generate our own resources. And we do have some sponsors, NASA headquarters, NSTRF, those of you who have any bright graduate students, real good program. The Air Force is giving us some money, and we're cost sharing with CEEE at Maryland. Go on again. So what are we doing? This is a component, this EHD component, EHD capillary chip system. This is silicon. So we're doing this on a 1 square centimeter chip. Basically what we're looking at is acquiring heat at high temperature. We're using thin film evaporation, very high heat transfer mechanism. Where it's going to be necessary, we will do some electric field fluid management, and we want to reject heat at to the lowest temperature sink, which a capillary-based system will choose it just based on pressure. But we also want to reject it at the highest possible temperature. That will save you on radiator space. Right? So we talked about that yesterday as well. So that's the tangible result that you get. So if we could move to the next chart. What's the embedded chip look like? This is the state of the art. We can move. This is a problem that we throw in our proposals. We're looking at a heat flux on the order of 630 watts per meter squared, but you're acquiring it somewhere in the order of 50. You spread it out. This is the state of the art. We have all of these different layers down to a heat pipe and out to a radiator. With our chip here, basically a capillary chip where we bring the fluid in by capillary forces, comes down, goes into a 90-degree chip with similar diameter, duct size, where the heat is acquired. We vaporize, and the fluid exits out from the chip out to the through the transport tube through the radiator. We're looking at more than doubling our heat flux and probably cutting our mass and volume by a half. So fewer components, lower overall thermal resistance, so we can acquire heat at a higher temperature and reject heat at a higher temperature. Both good things. Next chart, please. It's the multifunctional plate the Air Force is funding us to do. We're going to try to fly this on TechCube as a radiator. This geometry is probably no good anymore, but this is basically a plate with a series of ducts in it and some electrohydrodynamic pumps embedded in the plate. So this will be a multifunctional. It will be both structural and thermal control. And a radiator in the case, and we're also going to put on some advanced coatings on the outside because we have a guy who wants to do that, and he's not costing us anything. If we go on to the next chart, please. This is the STP-H5 experiment. This is the basic proof of concept or demonstration of concept of a multifunctional plate. Experiment delivery is upcoming. I really shouldn't be here. I should be back building this thing. And then the EHD experiment, we're going to demonstrate long-term operation of the EHD pumps and multifunctional structures. DOD is giving us the ride. The STP is Space Technology Program. And we're giving it to them in 2014, and it's being launched in 2016. I don't understand. It's just a long time, but that's the way it goes. Next chart, please. This is a schematic of the experiment. Next chart. More schematics of the experiments. Like my colleague yesterday, I've adapted an old talk for here because of the approval process. Next chart. This is the pump module. So this is what I want to show you. This is a mechanical drawing of the pump module. This is an EHD pump. What we have, and these pumps fit into this plate. This plate is, I guess, a couple inches by 3 inches, and we have 5 EHD pumps coming in through a manifold. So we have the fluid comes in here, manifolds out, pumps through, and goes out to the rest of the system. EHD pumps are nothing more than a series of electrodes. Geometry is everything. We apply an electric field to a dielectric fluid. You generate plus and minus radicals. The pluses go to the minus go to the plus, and the fluid has a net force forward. As you can see, this pump is pretty intricate. This is actually the second or third generation that we've worked on. We're down from a couple hundred parts to about 15 parts. And Matt and I have another generation of pumps where we're down to 2 parts. Basically just the electrodes, and then we're going to injection mold everything else into the pump. So that's how this works. Next chart. Thin film boiling experiment. This is some of our fundamental work. We're using electrohydrodynamic forces to pull the fluid into the center. We apply heat at the center. In gravity, there's nothing to make the bubble detach. There's no force to force the bubble. I mean, we have buoyant forces on Earth here. There's no force to make the bubble detach from the heat source. So what we're using is the inertial force of the fluid coming in 360, forcing the vapor off the heat source and replenishing the liquid so that we can continue the boiling process. This is very fundamental work. I'm doing this with Jamal Yagubi, or actually, yeah, I'm doing it with him. He's the PI. Let's make sure that we have that straight. And again, we're looking at the effects of gravity and the interaction of electric field and flow fields in the presence of phase change, which in other words, two-phase flow. Applications of this, again, we're doing this on the silicon disk, so obviously we're looking at electronics here as well. Next. This is pictures of the experiment. This is the 340-pound experiment that went on the Vomit Comet. I guess I should have brought a movie, but you really can't see much. And this is the experiment in operation. You'll notice this is a ceramic disc. We had a little trouble with the silicon discs before the flight, so we flew a ceramic disc. Doesn't change the science, just changes the substrate. This basically shows what we needed to show, that the EHD does help the heat transfer. It enhances the heat transfer, and it also showed that 18 seconds on the Vomit Comet is not enough to do long-term. We never reached the steady state, therefore we have to go to the International Space Station. This experiment, we actually did go to the science concept review. We got what I am taking as a positive report. They recommended strongly that we go forward with the experiment. Headquarters has to do their magic and let us know. In the meantime, we'll wait. So if I go to the next chart, please. This is really cool. This is something we did as a flyer, Hugh Bruck and I, and a very talented student named Alice Sauerbrunn, who is taking a job at Boeing, unfortunately. The idea is, how are we going to take stress, strain, and temperature measurements without having a bunch of thermocouples and strain gauges all over the place? And I know there are all kinds of ways of doing this. What you do is you take a non-conductive material, latex paint, you add some conduction to it, carbon nanotubes, which, by the way, adding carbon nanotubes to latex paint and getting it to stay in solution is a project in and of itself. And then basically you calibrate this material and you get a coupled thermal mechanical response. You have to divorce the thermal and mechanical responses, and now you can know stress and strain and temperature, taking up very little mass, very little volume, but now we're just moving electrons around. We can take this data to a processor, and we know when our system is getting ready to break. Probably sometime after I retire, but this project is, we're probably not going to finish this next year. But anyway, we've proven it's feasible. If we go to the next chart, there's a couple of charts just to show that, in fact, we can do it. Liz did this on aluminum, Invar, and a ceramic. So we had a variety of CT, coefficient of thermal expansion. just do this, and again, all that she showed here for her master's thesis is that we get some qualitative response that's in line with the forcing function. So I think that's the last of the charts that I have. I'm probably out of time, and there's a big question mark here like the Riddler, so I guess I'm supposed to take questions at this point. Thank you. Daniel. I think I'm reading it.
Yeah,
yes.
It's Dan. Dan from Tricept. I was wondering, are you thinking about using 3D printing technologies in order to build your radiators and that type of?
That's a loaded question. Yes, we would like to, but if we go back to the chart where the EHD, maybe not, where I show the EHD pumps, what we think the real application is where you have these geometrically difficult things, where you would have the, sorry
You've
about
got
that.
somebody else besides me does things like that.
Sorry about that. Okay. As you see here, we have a little bit of a geometric challenge, and the EHD phenomenon above and beyond everything else, and it's a whole dissertation basically, so I don't want to get into why it works, but it's a geometric issue. If we want to embed this into a duct, these tough geometries, there's no way to do this subtractively. So there may be some application, small scale, for that. The advanced manufacturing, 3D printing and stuff, it's kind of like the Wild West. There are no standards. Nobody knows what it does to the materials. I mean, essentially it's a series of laminar layers on top of each other, so I got to believe there's going to be some shear issues and stuff like that. But somebody in the room most certainly knows more about it than I do. Yes, the short answer is there's probably applications, but we're cautiously optimistic. Yeah.
I just want to, for the 3D printing.
Yeah.
Kennedy Space Center has a prototype lab,
Mm-hmm.
and they have a 3D printer, and then we've got some companies in the Central Florida community. Sure. Get with me, or I'll, because let's find out. Kennedy can help you design and test it.
Actually, one of the boys in the band, Matt Showalter, is the guy that I depend upon. If I knew it, I wouldn't need Matt. And my style is Matt's there, and he knows infinitely more than me. So we'll talk to Matt about the nuts and bolts of that.
Perfect.
Warren? Is it Warren?
Make sure he gets a mic.
He's got it.
Have you thought about applying some of this technology to terrestrial microcircuits?
Yes.
Yeah, that looks like a great way to cool a CPU.
Yes. That's also what we're working, my friends at Maryland and I are working very hard on that. That CEEE is a consortium of 30 industry-based companies. Some of them have electronics interests, power electronics. One other application for this that occurred to me is solar cells. If you can run the solar cells a little cooler, you get a little more efficiency out of these things. Embedding an EHD system, silicon-based, in the solar cell, if we can get 1 or 2% more, that might be important to the CubeSat community. Another 1 or 2% power. I mean, it may only be a tenth of a watt or a couple tenths of a watt, but last I checked, we're counting everything. So maybe that little bit of power does something for somebody.
Do we still have time for questions?
Sure.
Okay. When could these potentially be available for deep space CubeSats, and what are the implications in terms of resources needed for the design?
I will defer the question to something Matt says and something Warren Zevon said, and lawyers, guns, and money. We can do anything you want with enough time and money.
Well, okay,
but it would take, for example, the chip. I have a 3-year plan to have the silicon ready to go, and that would include the TechCube flight next year and another flight to do the optimized system after. So it's 2017, I think, with sufficient resources.
That's interesting because it's the day when that's the year we're supposed to launch the first deep space CubeSats from EM1. So.
Yep.
Okay. Thank you. We'll talk more about this in the lunch challenge.
Sure.
So can you? Oh, I'm Courtney from JPL.
Sure.
Right. Can you give the 2-sentence contrast between this technology and things like heat pipes?
Yeah, I mean, heat pipes, it's a capillary phenomenon. So that has that limitation. Actually, I view them as complementary. This is electric field-based phenomena. So we use electric fields to pump fluids, but we can also manage fluids with that. So the pumping of the fluid is electrophoretic. The management of the fluid, in other words, liquid vapor, putting liquid and vapor where you want, is the use of the dielectrophoretic force.
So in some design, you might use them both.
Oh, I anticipate that.
Okay.
Yeah, and there was one other question, this gentleman right here.
Jeff from
Yeah.
MMA. Maybe concentrated solar arrays, especially for this, where you've got smaller area cells with massive thermal loads.
Absolutely.
Is a good application
Yeah.
versus a conventional area.
We're always open to that. I just know what comes through my lab, so I'd be interested in hearing about that. And I think somebody's about to get the shepherd's crook out on me here. So, okay, 2 minutes. Anybody? This gentleman right here. Walter?
Yeah.
Yeah, thank you.
Has anybody asked?
First of all, who are you?
Walter
Sorry.
Burns, PSC. One of the exciting parts of interplanetary exploration of CubeSats is to use electric propulsion. Have you had the opportunity to apply this technology to cooling those engines? We're talking about 200 watts in a 6U.
No, but we can. I mean, you know, we're thermal guys, and we reduce everything to heat fluxes and other various, you know, critical parameters. So I don't see any reason why we can't. And that would actually be a very good application, because if we're talking about the multifunctional structures and things like that, you know, we could probably put the cooling inside the tank. Now, having said that, conductivity is a big issue for us. So, you know, we have to insulate the hell out of these electrodes and things. But all of those problems can be solved, which led to somebody's question about the additive manufacturing, and that's another area where I see it. Also, back to your question, the additive manufacturing, this stuff about the self-sensing, nano-enhanced polymers, that would really be cool if one of your layers inside of the laminate buildup of an additive manufacturing was the self-sensing layer, because then you take away a lot of interfaces. So actually, that's the idea I really like a lot. It's very intriguing.
One thing that has me going about the nano-enhanced polymer is potentially going into force feedback control.
Yes.
For structures. So
Optimized systems operation, neural networks, the whole drill. That's what I envision this going.
And active elements. Excellent.
Yeah.
Let's talk.
Yeah.
Right.
Need a bigger team than me, and I'm being thrown out now. So thank you very much for your attention.
Thank you, Stephanie.